Hello, and greetings from Rutgers. James Abello and I, Daniel Nakamovich, would like to present to you graph waves, a means of visually exploring large graphs. But what does it mean for a graph to be large? For computers, we consider a graph to be large when it doesn't fit in random access memory. But for us humans, we are further limited by how much we can perceive. This is partially due to the physical constraints of our screens, but also the computational ability to allow a user to manipulate layouts in real time. Thus, a desirable graph exploration system should be computationally efficient for large graphs while providing interactive control without overwhelming the user. Previous work proposes a decomposition algorithm that partitions a graph into sets of edges called fixed points of degree peeling. These fixed points are visually represented as layers in order to break a large graph into meaningful and manageable chunks. As the name suggests, however, the same decomposition cannot be used to further decompose fixed points. So, to deal with large fixed points, we propose a new decomposition into graph waves and fragments. Similarly to how fixed points form an edge partition of a graph, waves form an edge partition of a fixed point. Waves are constructed from a sequence of fragments in the following way. Given a fixed point with minimum degree k, we take the vertices of degree k as an initial seed set. In the example on the left, we have a fixed point of minimum degree 2, and the initial seed set is S1 circled here. The edges with at least one vertex in the seed set are labeled as the first fragment and removed. Here that would be the blue edges. Once removed, the degree of the fragment vertices that were not in the seed set are updated, and those with degree less than k are selected as the next seed set, S2 in this example. Again, we label the edges going out of the seed set as the next fragment, remove them, and update the degrees of the affected vertices. We repeat the process until there are no remaining vertices, or the remaining vertices have degree equal to k. All the edges removed so far are labeled as the first wave. We start again with a seed set of degree equal to k and repeat the process until the fixed point is empty. In the left example, the blue and green edge fragments make up the first wave of a fixed point of minimum degree 2, and the red edge fragment makes up the second wave. The picture on the right shows a collection of 19 fragments colored blue to red from a wave in the Friendster social network. Using the wave decomposition, we can represent fixed points as wave buildings. The volume of each double frustum corresponds to the number of edges in the corresponding wave. This provides a visual map of fixed points, allowing a user to select subgraphs of a fixed point for further inspection. When a wave is still too large to view directly, one can further navigate through its constituent fragments. In this example, the last wave, colored red, has 4.3 million edges and can't be displayed interactively. Instead, a choice of fragments is presented to the user, and in this case, they select the 40th fragment displayed on the right. The structure of graph drawings of moderately sized fixed points and waves are not always easily interpretable if drawn with naive layouts. Assigning directions to edges between fragment seed sets, going from lower to higher, we can construct a directed acyclic graph that contains a subset of the edges of the original fixed point while including all of its vertices. We call this structure a DAG cover. It can be used to enhance the drawings of fixed points and waves by reducing edge clutter, informing choice of color, and controlling forces for physics-based layouts. The example on the right is a fixed point from the Friendster social network of minimum degree 22, which has 30,653 edges, but whose DAG cover only contains 5,859 edges. We also designed a global spiral view of a graph by grouping fixed points into buckets according to the number of edges. Each bucket is represented with a thumbnail and provides direct access to any group of similarly sized fixed points in the graph dataset. The color of each thumbnail encodes the average density, blue to red. Two types of buckets are shown on the right. If a bucket has many fixed points, the thumbnail shows a polar bar graph of the distribution of fixed points. If a bucket has only one large fixed point, then the thumbnail shows a 2D wave map, which is similar in style to the wave buildings. Our current work includes exploring the semantics of waves to gather insights into the practical application of the wave decomposition. The picture on the right is a fragment from a patent citation network. We show the category and publication dates for a few patents, all related to chemical and medical processes. We are also designing a new method of global graph navigation. By visualizing a unified space of fixed points represented through wave buildings, we hope to give the impression of navigating through a futuristic cityscape. Thank you for watching this presentation. I'd like to thank my colleagues for helping to implement various aspects of our system and NSF for supporting this project.